let's first review or recap what we learned last week. Last week we first discussed the binary ASK and BPSK and FSK, right? So those are three different bandpass modulations, digital bandpass modulations. So this is ASK. As you know, we have binary symbol 1 and 0. So when you have binary 1, you have some energy. 0, you have no energy. So that's why we call this one as on-off keying, right? And whenever you have a binary 1 and you have energy, what you want to do is you multiply carrier onto this, right? So the carrier we are using is a sinusoidal cosine carrier with the carrier frequency Fc. So when you multiply the carrier onto this Bt, this is St, what we transmit, right? St is what we transmit over the air. So this is the signal that you are transmitting for binary ASK. So whenever you have a symbol 1, you transmit cosine. When you have 0, nothing, right? That's the BASK. However, BPSK has the information on the phase, right? Because this is a PSK, meaning that the phase is changed depending on the information. So if your original information is 1, let's say this is symbol 1, that means you are transmitting cosine with the phase 0. When you have a symbol 0, in this case it's the same cosine, but you have a phase difference, phase 180 degree. So symbol 1, phase 0, symbol 0 means phase 180 degree. So we have two different phase 0, phase pi. So that's the phase shift keying. But since the phase 180 degree basically means that it's minus cosine. So it ends up like cosine and minus cosine, plus cosine, minus cosine. So that's antipodal signaling, right? We learned that. So this BPSK has exactly the same as antipodal signaling, right? This is a block diagram for BPSK transmitter, BPSK receiver, right? Anyway, the original information is the binary bits, 1 or 0. And now that's coming in. Binary data stream means the bit stream, like 1, 0, 0, 1, 1. This is the bit stream coming into the transmitter. Inside the transmitter, what we need to do first is a symbol mapping, bit to symbol mapping. This is what we do, right, in the mapping. So you can do this mapping, that's okay. Right? So this is the mapping. Whenever you have a 0, you map into minus symbol. When you have a 1, you map it to plus symbol. Once you map it, now we're going to get symbol here. Symbols. Here we have bits. Now everything is mapped to symbols. That's what we have as a BT, right? Now this BT is multiplied with a carrier. This is a carrier CT. CT equals to this. This is a carrier. So once you multiply this BT, one of these, right? This is a BT, right? Minus root square EB or plus root square EB, that's BT. On top of that, you multiply the carrier, eventually you are going to get ST. And ST is going to be this one or this one. So based on this mapping, now you can see that if the original information is 0, then based on this mapping, 0 is mapped to minus root square EB. So eventually, after all this process, you're going to see this output, minus cosine, right? However, when you have information 1, original bits is 1, based on this mapping, you're going to see this positive cosine at the output of the transmitter. So this is what we transmit over the air, plus cosine, minus cosine, depending on 0 or 1, right? That's what you transmit over the air. Now suppose that we have no noise, channel is perfect. In that case, this signal is now coming into the receiver. So if this signal coming into the receiver, what we need to do first of all at the receiver is to multiply carrier, the same carrier again. right? That's same as in analog communication, right? In analog, you also do the same thing. You multiply the carrier just before transmission. At the receiver, right after you receive the signal, you multiply the same carrier. So therefore, our carrier is cosine. So you multiply the cosine and then transmit. This signal is now received, and you multiply cosine again. So right here, you're going to see the cosine square. Okay? Every time, right? Analog, digital communication, same thing. You're going to see cosine square right here. So every time when you see the cosine square x, you're going to see something like this. Every time when you see this, you have to remember this identity. Okay? You have to remember this identity, right? And based on this identity, what you can notice is that you always have a cosine 2 times of frequency or phase. It is x. X is a 2 pi FCT, right? You have a frequency, the carrier frequency right here. And you're going to see that the 2 times higher frequency, which means higher frequency, right? So that's why every time when you multiply cosine, you have low pass filter. Okay, every time. Why do you have low pass filter? You're going to remove this. That's why you have it all the time, every time. Right? Every time when you use the over-the-air communication, you use cosine as a carrier. Since you use cosine as a carrier before transmit, at the receiver, you also multiply the same carrier. See that this is the exactly same carrier, right? Same carrier again to make a cosine square. When you have a cosine square right here, you always see that cosine square is actually same as a DC plus high frequency. That's equal. Okay, that's equal. And what you want to get is a DC component. That's eventually what you want to get. You don't want to have high frequency. That's why you have low pass filter every time. This one, right? We see that the product modulator, same here, product modulator. So this is actually multiplication. But in a lot of times, when you talk to the hardware people, those people, hardware people, mention this one as a mixer. Remember that frequency mixer. This is actually frequency mixer. You can say that product modulator, mixer, multiplier, all the same thing. Okay. Some of you who took my the communication course last semester, we talked about mixer many times, right? Remember? Yeah, mixer is important, very important. And just remember, simply speaking, every time when you have a mixer, every time when you use a mixer, you should have filter right after that. What was the reason? We discussed this many times last semester. Very simple. Think about the mixer. Let's say here is a mixer. What is a mixer, by the way? Mixer is getting 2 inputs, 2 frequency inputs. Like let's say cosine 2 pi f1t. Here we have a cosine 2 pi f2t. Just the example, okay? Just the example. Every time when you see the mixer, this is actual hardware. Actual hardware. Actual hardware called the mixer always gets 2 inputs. And you're going to have only 1 output, typically. Sometimes you get 2 outputs, but generally you're going to have 1 output. And what output do you want? Why do you want to use a mixer? The main reason you want to use a mixer is to make another frequency. You want to make a new frequency. You only have a F1 frequency, you have F2 frequency, but you want to get a new frequency. For example, this, or this. This is what you want. You want to make a new frequency. That's why you use a mixer. Okay? That's the reason we need a mixer. Then how do you make this new frequency? It's very simple, right? Think about this. This is a hardware called the mixer, but actually the operation of mixer is a multiplication. So let's do multiplication. This is cosine, first input, another cosine, second input. So simply multiply these two. This is what's happening inside. So just multiplication. But we know that this multiplication of cosine, 2 cosine, is actually same as cosine 2 pi f1 plus f2 t. Is it minus? I think minus, right? 2 pi f1 minus f2 t. Do we have 2 or not? No? Is this right? Huh? 1 over 2? Yeah, I forgot that. So based on the identity, we can just rewrite this one into this way. I didn't change anything. I just used the identity. This one is actually same as this, right? So whenever you multiply or mixing 2 different frequencies, what's actually happening inside the mixer is that you create 2 different frequencies. Okay? When you multiply 2 frequencies, naturally, when you multiply 2 different frequencies, it is actually creating 2 different new frequencies, f1 plus f2, f1 minus f2, 2 outputs. But let's say I want to get this, because there's only one output. Let's say I want to get this. Then how do you do that? You want this, right? Then what do you need to do? You have to remove this. How do you remove it? Filter. You need to use filter. Okay? It's going to be band pass filter in this case. So that's pretty simple. So simply speaking, why do you want to use a mixer? What is a mixer for? Mixer is typically used to make another frequency. But now, let's think about a little bit special case. This is a general introduction of mixer, but let me just change it into 1. Same frequency. I can put the same frequency, right, for both of the inputs. That's actually what's happening inside. That's the same thing. So I can just do that. There's 2 inputs. I can put the same frequency into the mixer. In that case, what's happening? In that case, this is going to be F1. Here's also F1, right? F1, F1. So you're going to get 2 F1 or DC. You're going to get 2 outputs. And which one do you want? In our case, we want this. You need to remove this. That's why you need a low-pass filter. Okay? So simply speaking, every time when you use a mixer, you always need a filter. You always. Okay? You always. So simply speaking, when you put these whole together, multiplier, filter together, this is like a mixer hardware. Okay? So you're going to get a DC back after low-pass filter, because after low-pass filter, this high-frequency component is gone. Now you sample it, you make a decision. As I said, the reason that you need this decision block is because that in most cases, you're going to have noise. In this block diagram, it's so simple that we ignore the noise. But actually, in the real system, this is what you transmit. But over the channel, there is a noise, right? So you're not going to receive this. You're going to receive this one plus noise. That is coming into here. So that's why, because of this noisy signal, things are not that perfect. So that's why you need the decision block later. Okay? Because there's a noise. Noise also going through, right? So please remember this picture. this? Okay, so suddenly computer's turned off. So let me reboot. Okay. Okay, so please remember the QPSK transmitter and receiver. And what you need to remember is that before the transmit, you always multiply the carrier, cosine 2tb root square cosine 2 pi fct. And we have the input bt to the modulator. And after you multiply the carrier ct, eventually you're going to transmit st over the air. Right? And at the receiver, you receive the st, this st coming into the receiver. Now inside the receiver, again you multiply the cosine, the carrier, right? And every time when you have a mixer or multiplier, you need to have a low pass filter. And then you want to get the DC component only. Right? Yeah. And once you put the low pass filter, you're going to get only the DC component. And your information is in the DC component. How do you know? Because this is DC. Your original information is the DC. When I say DC, that means a baseband. This is baseband. Okay, remember this word. This is a very common word. Baseband. And here is a passband. Every time when you multiply the carrier, that becomes passband. So over the channel, over the air, it's always passband. You have your own frequency. So what's the frequency in the passband? What's the frequency of the signal? FC. Why? Because we multiply carrier frequency FC, right? So you're going to see FC frequency. So when I draw this in the frequency domain, this is the whole frequency domain. Here's a 0. Your original information is in the baseband. So your original information starts from here. This is where your original information is, right? Your original information is around the DC frequency. This is the area we call that as a band pass. Now, starting from band pass, what we do is that we multiply that with the carrier frequency, right? Once you multiply the carrier frequency onto here, once you multiply carrier frequency, now then this is shifted into here. So frequency domain point of view, this signal in here, BT, is now moved to passband signal. So the ST actually has this frequency component, right? This is what we receive here. And you're going to multiply cosine again. Now there's this signal going back to baseband. So here, you're going to get only the baseband, right? Some of those things you need to remember. So this whole procedure is exactly the same as our analog communication. Okay, I think we probably want to review these things. Some of you remember these things. We discussed this frequency picture many times last semester, but I guess some of you probably don't remember. So let me review those things first. What you see in this picture is a whole time domain, right? In time, you do this first, and later you do this, and do this. Everything is sequential. And this is a time domain signal. In time domain, let's draw this one. Sometimes you have a plus cosine, sometimes you have a minus cosine, plus cosine, minus cosine, something like this, right? That's what you transmit over there, but this is a time domain. Same that time domain signal coming into here, and everything is sequential. Now let's take a look at the whole thing, the same picture from the frequency domain. This signal right here, or this signal right here, we are in bandpass, baseband, not bandpass. We are in baseband. And when you draw this BT in frequency domain, it's something like this. When you have this signal in baseband, now you multiply the cosine into here. Then what's happening here in the passband signal? What is happening? What is happening is you're going to see this kind of frequency picture, right? Which means that the original bandpass signal, original baseband signal, original baseband is now moved into here and here, right? So this is what ST looks like. 이거 전원이 꺼져 있었구나. 이거 전원이 꺼져 있어. 배터리가 나갔나 보네. 근데 전원을 꽂았는데 전원이 안 들어와 있네. Okay, let me just draw it here. So we have a BT here, right? BT. So we have a BT. BT comes into here, and we multiply a carrier CT. The CT, you know, is a cosine, right? 2TB root square cosine 2 pi FCT. That's what you get as ST. So when you draw the ST in the frequency domain, this is what you're going to get. When you multiply cosine into here, then the original energy in here, in the BT, this is the BT, right, in frequency domain. Original energy here is now split into positive FC, negative FC, half and half. Half and half. So this is what you see for the passband signal. This is a frequency picture of ST. Now at the receiver, we're going to receive that. Okay, that picture. We have a minus FC and plus FC, 0. This signal now comes into the receiver. And what's the first thing to do at the receiver? The first thing to do at the receiver is that this ST comes to the receiver. First thing is, again, you multiply carrier. You're multiplying this carrier. So right after you multiply carrier, the signal in the frequency domain is going to be what? So now this one needs to be changed. How does it change? Same thing happens here. When you multiply cosine, what happens? The energy here is now split into two parts. That's what happened. Half energy left, half energy right. Split like that. That's what happened, right? You're going to multiply same thing. You're going to multiply cosine again. But now difference is that you are multiplying cosine into here. This is the input. You multiply cosine into that. Then what's going to happen? Same thing happened. This one is split into half. That one also split into half. So what's happening? This is what's happening. What does it mean? Think about it. Split half and half. So this one now split into half and half. This one also split into half and half. Then this one goes into 2FC. This one goes into minus 2FC. And this half of this energy goes into 0. Half of this energy goes into 0. So 0, you're going to have a little bit higher energy. This one, small energy. So somehow you're going to have 1/4 of energy here, the half of the energy here. That's what you're going to get. Right? So this picture is what you're going to see at the output right here after multiply the carrier. I'm talking about frequency point of view, right? This is a frequency picture. Now, what is the next thing to do? Low pass filter. So when you put the low pass filter now, what happened? Your low pass filter will look like this. This is your low pass filter. So your signal in baseband will pass, no problem. This will be dropped. So eventually, after the low pass filter, what's going to be the output? Now you're going to get this as the output, which should be same as this. Okay, that's the whole process. Okay. So your original information. Your original information is in the baseband, meaning that it's around the frequency 0. When you multiply cosine, your signal moves to the passband. Okay, so the energy is split, and your signal is around your carrier frequency. That signal is received. You multiply cosine again, so each one is now split. This one also split, right? And then half of this energy comes in here, half of that energy comes into 0, comes into the baseband. So that's what you have here. And some of the energy is to the 2FC minus 2FC. This is why here you see cosine square, right? What you see here is actually cosine square. That's a cosine square. When you have a cosine square, when you have a cosine square, you see the DC term, you see the 2FC term, right? Remember? Every time when you have cosine square x, it's going to be like half 1 plus cosine 2x. This is why. You have a cosine 2x, and you have a DC component. Okay? This is actually cosine square in frequency domain. Now, after that, what do you need to do? We're going to only get this one. We don't need this. Okay? We only want this. That's why put the low pass filter, remove the 2FC term. Now you're going to get only this one. Okay? So please remember that block diagram, also the frequency point, frequency picture. So you need to remember this whole block diagram, okay? How the transmitter works, how the receiver works, every point, okay? What's happening in every point. Please remember that. Also, please remember this frequency picture for every point. Every point. Okay? This point, we have this frequency. This point, we have this frequency point, this frequency picture. Right here, we have this frequency picture. And when you go through the low-pass filter, eventually you're going to get this right here. Okay, so please remember every single point, what's happening in frequency domain, time domain, and what is the operation of mixer, all these things. Please remember that. Okay, it's very important. Okay, now let's move on to the next thing. And next thing we want to talk about is a QPSK. We already discussed the QPSK. Simply speaking, this QPSK is an extension of a BPSK. So far what we learned is a binary PSK. So we need only 2 different phases. But here in QPSK, we need 4 different phases. So it's like a 0 degree, 90, 180, 270 degree. Okay? Simply speaking, those are 4 different phases. But the more common QPSK is this signal. So this equation is simple equation to tell you what each symbol looks like. We have I should be 1, 2, 3, or 4 because we have 4 symbols. So simply we have S1, S2, S3, S4. We have 4 different symbols, possible symbols. Okay? And what you can see in this picture is that we know that the cosine, we use the same cosine carrier, 2 pi Fc. Fc is a carrier frequency, same as BPSK. Only difference between BPSK and this QPSK is this term. In the BPSK, right here we have 0 or pi in BPSK. Right? However, now in QPSK, what we have here is 1 over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. That's only difference. That's only difference. So we have you can easily get this, right? Because I said I equal to 1, 2, 3, 4. So put the 1 here. Now you're going to get this. When you put I equal to 2, you're going to get this. 3, 4, right? So you're going to get these things. So that's it. That's it. Okay? So this equation is pretty simple. Same as BPSK, only difference is this part. Now, when you look at this, right, this is cosine alpha plus beta. And cosine alpha plus beta equals to cosine alpha cosine beta minus sine alpha sine beta. This is another identity we learned in high school. So use this identity, nothing changed. Use that identity to change this equation into this. This same thing. Here's alpha. So we have alpha here, cosine alpha. Here's a sine alpha. The second term here is a beta. So we have beta here. We have beta here. So cosine alpha, cosine beta minus sine alpha, sine beta. So just simply replace this, right? Now once you do that, we can see that this is a cosine carrier component, pure carrier. Here is a sine pure carrier. Okay? Carrier, we don't worry about it. Why is that? Carrier is only necessary in the channel, only necessary to deliver your signal. Think about here, right? You multiply the carrier just before transmission. Now, after receiver, you multiply carrier. Once you multiply carrier at the receiver, now carrier is gone. Here your carrier is gone, right? So your carrier is only necessary to transmit over the air. And everything else, you don't need a carrier. So carrier is not inside your processing. Carrier, you don't care much. So this one, carrier have no information. Okay? Think about it. You have your package. You want to send this package into your friend in Canada. You don't care about the carrier. Maybe you can use a DHL. Maybe you can use FedEx. Those you don't care, right? Whatever carrier you use, don't care. What is important is your package, your information. Here, carrier, you don't care. What is important is this part and this part. This is what is important. Okay? That is what is important for you. That is important. This is the information for the cosine carrier. This is the information in the sine carrier. Okay? Forget the carrier part. It's not important. Your important thing is a beta term. But when you look at this beta term, what it is that this is simply cosine phase, cosine some phase. And this phase is actually this one, right? When I equal to 1, it's going to be like a cosine 45 degree, sine 45 degree. When I equal to 2, cosine 135 degree, sine 135 degree, something like this, right? That is the important thing. So in order to see this whole thing easy to look at, now what we're going to do is that we're going to draw the constellation plot. So that's why we need a constellation plot, in order to see this whole thing easily. So let's draw the constellation plot for the whole thing. Every time the constellation plot, you're going to start from here, and then rotate this way or this way. It doesn't matter. Okay? It doesn't matter how to rotate. Because what is important is a relative difference. In this picture, I think what they are doing is rotating this way. I think that's what they are doing here. So we have unit circle. And S1, let's take a look at the S1. S1, you have a positive 2e divided by t root square cosine pi over 4. That's a cosine term. And in sine cos term, minus 2e divided by t sine pi over 4. So that is S1, right? S1 is the cosine carrier term, you have this. Sine carrier term, you have this. You have a minus here, right? So let's plot this into this constellation plot. Now, I'm not going to plot this cosine carrier, sine carrier. Why is that? Because I said this x-axis is a cosine. This y-axis is sine. Okay? So this one, alpha term, will indicate which axis you use, x or y. So you are not drawing this. This is not information. Your information is this part. This part is your information. This thing is your value. Okay? So what is your S1? S1 equals to this and this. And you know this is 45 degree, right? Root square 2. 1 over root square 2. Because this is 45 degree. Right? So when you plot this, it ends up being here. Because that's a positive, negative. So positive in cosine, negative in sine. So we have S1 here. Let's take a look at the S2 now. S2, same way. S2 equals, same thing. Let's look at here. S2 equals 2e divided by t root square cosine 3 pi over 4 minus 2e t root square sine 3 pi over 4. So that means we are here. How do you know? Because from here, we are always starting from here. 45 degree means we are rotating that much. Only 45 degree. Only pi over 4. But in this case, you are rotating 3 pi over 4. So we are rotating this much. So here to that much is a 3 pi over 4. So we are rotating that much. Same way, you can keep doing it. Here is S3, here is S4. You can actually easy to see it, right? What is this value? I mean, what is this value? Cosine 3 pi over 4. This is 135 degree, right? What is a cosine 135 degree? Let's draw cosine. Here's a cosine. We have 0, 180, 360 degree. And here, 0 crossing point, this is 90 degree. So 135 degree is somewhere here. So it's a negative value. So in fact, this is negative. So that's why you have a negative, cosine negative, sine also negative. So you see that. This is where you have S2. Same way you can do that. S3 has this phase. So you are rotating that much. S4, we have this much phase. So S4 is going to be like this much rotation in phase, right? So eventually, you're going to get this picture. S1, S2, S3, S4. So that's the picture for the QPSK. Okay. So simply speaking, let's go all the way. So this is a picture eventually you're going to see. Let me draw this one. This is going to be a picture. This is what we call as a constellation plot. We have 4 symbols, right? S1 here, S2 here, S3, S4. So we have 4 symbols. Each one has these much phase rotation. And what is this energy? This energy? What is this value? This is amplitude. Amplitude of your S4. Actually, this is a circle. So all these 4 symbols have a same amplitude. So what is this amplitude? Root square E. Actually, just forget D. I think this is wrong. We should say E over 2. Okay, this is mistake. Okay, misspelling. So we should say E. Or maybe we can say ES, not EB. Okay, EB and ES is different. So in order to make a correction, we want to have ES. ES and E, same thing. So here we should have ES, root square ES. So this value, amplitude, should be root square ES. Why is that? ES is your average symbol energy. Average let's see. Yeah, average symbol energy. Yeah, right. ES is average symbol energy, which means that your symbol has a certain energy in average, right? That's ES. But what you see here is not energy. This is amplitude, not energy, right? So what you need to do is you need to put the root square in order to get the amplitude. This is the amplitude of the signal. Your signal always go up and down, right? You have an amplitude. However, energy is not the same as amplitude. You need to do square. Then you're going to get the energy. So if ES is the energy, amplitude should be root square ES. So this value right here, the radius of the circle, is going to be root square ES. When you have a root square ES for the amplitude, what's going to be the point here and here? We're going to get this, right? Because this is 45 degree. So this point right here, you can read it like ES over 2, ES over root square 2. So that is your point here, right? Because the amplitude is this. That's what we can see here in this picture. Now then, how do you get it? Let's go to this slide. This slide is actually talking about the same thing. Okay, let me go back one more slide here. As I said earlier, what is important is this part and this part, right? That is important. Okay, this part is important. So let me get only these parts. Forget the carrier, forget the cosine carrier, forget the sine carrier. Only take this part and take a look at a little bit more detail. That's what you see here. That's what you see here. That's this part. That's this part. Okay? That's this part. Now this value is going to be either this one or this one, because this is simply cosine anyway. So sometimes when I equal to 1 and 4, you're going to get positive value. But when I equal to 2 or 3, you're going to get the negative value. You can easily see it, right? When you have I equal to 1, your cosine will be positive. And when I equal to 4, again positive. But when I equal to 2 or 3, your cosine will be negative. Like that. Same thing for sine. When I equal to 1 or 2, you get sine, minus sign. When I 3 to 4, you get the positive sign. So that's what you have here. Okay? Nothing difficult. That's what you have here. One more thing that I want to discuss with you is these things. These things. What it says is that cosine, this is a cosine carrier, and we have a sine carrier. Cosine and sine carriers are orthogonal each other. It is red, right? Meaning some important things. Why is that important? Now let me go back here. You know, this is a ST, S1, S2, or S3, S4. So meaning that this is what we transmit over the air. In QPSK, this is what we transmit over the air. So you are transmitting this signal over the air, but in your signal, you are actually transmitting two signals. You are transmitting this, but you are actually transmitting two, because we have one here, another here. We have two terms, right? We have a transmitting cosine signal, we are transmitting sine signal. Now think about that. You are transmitting, how can you transmit two different signals? This and this. And what if you have, what if the cosine and sine carrier are not orthogonal? Then what's going to happen? There will be interfering each other, because you are transmitting two signals. And if this signal are mixed, basically, right? You are mixing and transmit. If these two signals are not orthogonal, that means you are interfering yourself. You are making two, but they are interfering, right? You are making interference. So that's not good. Nice thing about this is that cosine carrier and sine carrier are always orthogonal. So that means you can mix these two, no problem. Because at the receiver, you can always separate with the interference 0. So in this case, you can add these two as much as you can. Perfectly fine. That's why you have this cosine and sine is added together and mixing together and transmit at the same time. And cosine and sine are perfectly orthogonal. How do you know? How do you check the cosine and sine are orthogonal? You product and do what? Integration. You're going to get 0. Right? You're going to get 0. Is it really true? I mean, let's do that. Cosine x, sine x. You multiply these two. What is the condition of orthogonality? Orthogonality is that, let's say, if fx is orthogonal, with the f1x and f2x is orthogonal, that means f1x times f1x, integration, that should have some value. And when you multiply these two signals and then integration, you should get 0. If that is orthogonal. This is the condition, right? What if that you multiply these two and integration, do you get 0? Yes. You're going to get 0, right? How do you know? When you multiply cosine and sine, cosine x, sine x. Again, we have to use the identity. Cosine and sine, it's going to be half. Is this sine? Sine what? 2x plus sine 0? Is that what? Is that right? Or cosine? Is it cosine or sine? But actually it doesn't matter, really, because it doesn't matter. Because what is important is that when you multiply cosine and sine, you have a FC here, right? But eventually you're going to get 2FC somewhere, and you're going to get 0 somewhere. And when you integrate, 2FC is gone anyway. Okay? Because you are multiplying a period. This is gone anyway. So you're going to get 0 anyway. So cosine and sine, when you check the orthogonality, it always gives you 0. It's always orthogonal. So that's why you don't have to worry about interference between each other. You always mix together and make 2 different signals and combine, transmit. Perfectly fine. Okay? So that's why we use this QPSK using 2 carriers. It is actually the same as making cosine signal, transmit, making sine signal, transmit. Mixing together, transmit. Okay? That's what we are doing in the QPSK. So this table summarizes the value. This table summarizes the value. What value? What is this value? This is the value of cosine carrier. Think about this whole thing as an x and y graph. Okay, if you read this one as an x and y graph, this is x value. This is y value, right? So what is S1? Here's S1. S1 has the 45 degree. X1 has this x value, this y value. That's what you see here, right? X and y. That's this and this. Here's S2. S2 has a minus x, minus y. That's exactly here. So this is summarizes of x and y value in the constellation plot. Okay, constellation plot. Now there's one more thing to talk about here. This one and this one is simply x and y for each symbol, S3, S4. We already learned about gray coding. Remember the gray coding? What is the gray coding? Gray coding is how to map bits to symbol. It's a bit to symbol mapping, right? What we are talking about here is just a symbol. We have 4 symbols, symbol from S1 to S4. These are all symbol. Now the question is, how do you map bits to this symbol based on the gray coding? That's the question, right? And you see that this is the mapping for those things. And what is the gray coding? Let's take a look at here. S1 is mapped to 1, 0. This one has the bit 1, 0. Let me look at this picture. That's easier to look at it. So you'll see that this is a mapping based on the gray coding. So if you want to map 1, 0 here, this is S1. This S2, which is neighboring, this is neighboring symbol, right? This neighboring symbol should have only 1 bit difference. That's gray coding. So here's 1, 0, then this one. Maybe you can do 0, 0 or 1, 1. Anything is fine. Maybe you can choose either one is fine. Okay? You can do this one. But 0, 1, you should not do that. Because this is neighboring. If you select the 0, 1 for this, now we have a 2-bit errors, right? So that's what we should not do. So that's gray coding. What about this one? This is also neighboring. It's the same thing. This one is a 0, 0 or 1, 1. So if you pick 0, 0 for this guy, then you can pick 1, 1. Or 0, 0 here, 1, 1 here. Either one is fine. So once you have a 0, 0, 1, 1, this one, definitely it's going to be 0, 1. This is a gray mapping, right? Gray coding. So based on gray coding, this picture, this constellation picture, look at this picture. This picture tells you many things. First of all, we have 4 symbols with this much of phase difference. That's one thing you can see from this picture. Second thing is mapping, bit to symbol mapping. That's another thing you can see from this picture. Okay? And also the value here, the energy, amplitude. So that's another thing you can see here. So from this constellation plot, you can see all of those things. One thing that you are not going to see from this constellation plot is there's no t, there's no time. Okay, time concept is not in this constellation plot. When you look at the previous picture here somewhere, you have a divided by t, you have a t somewhere here, right? But t is not in the constellation plot. Time doesn't matter. Why is that? Because remember, right? I told you something like this. Maybe you can think about 2 different scenarios. In some scenario, t is short. Some other scenario, t is large, right? But as long as we have the same energy, Es, it doesn't matter. Maybe in this case, this whole thing is Es. In this case, this thing is Es. So what is important is energy in this picture. Okay, this picture don't care about the t. As long as you have the same energy, this picture is the same. Okay? T doesn't matter in this picture. This is how to generate the QPSK signals. Okay, this is how to generate the QPSK. How many bits do you need to get in QPSK? You need 2 bits, right? Every time you need the 2 bits, maybe 0, 0 or 0, 1, something like this, right? So you need to get 2 bits for the input. So bit sequence coming in like 0, 0, 1, 0, something like this. You're going to get bit sequence. Now here, what is this block? You have the same block in BPSK, right? Its name is same. So what is this block? This is a mapping. Simple mapping between bits to symbol. So we get a BT again, right? BT here. Okay, just want to remind you. Let me go back to the BPSK picture. This is the picture we looked at, right? We have a bit sequence coming in. This is the mapping between bits to symbol. We have a BT here. BT is a symbol sequence. Exactly the same thing. Exactly the same thing is in QPSK. Exactly the same thing. We have a BT again. This is symbol sequence. Input is a bit sequence. So we need to do bit to symbol mapping. So what is going to be the mapping in here? This mapping is based on this picture. Whenever you get the bit 0, 0, now what is going to be the output of the mapping? This is the output of the mapping. Whenever you get a 0, 1, this is the output of the mapping. Then what does that mean? Then what is exactly the output of the mapping? Let me go back to the BPSK. In BPSK, what was the mapping of BT? What is the output here? This one or this one? That was the output here. Then what is the output in QPSK here? What does BT look like? BT? What does it look like? This BT now have a 2 value because we have 2 carriers. So let's say, as an example, let's say we get a 0, 0 as an input. So we have a 0, 0 input. Based on this mapping, the output is this value in cosine, this value in sine, because this is the mapping, right? So that is the That is a cosine value, that is a sine value. So what BT looks like here is two value. This one and this one. So this one is a minus this root ES minus ES divided by root square 2 minus ES also minus. So we're going to get this output here. Right? We're going to get that output. And next bit sequence, we're going to get 0, 1. Let's say 0, 1. 0, 1 is coming in. When you get 0, 1, then what is going to be the output? Here is a 0, 1, right? So our output in that case is going to be this value in cosine, this value in sine. So when you get, this is the output for 0, 0. Whenever you get a 0, 1, your BT is going to be minus ES over root square 2, positive. This is going to be your BT for the input 0, 1. Okay, that's how you get as a BT. Right? So you're going to get two value here. In QPSK, everything is only in the cosine axis. That's why you have only one value. But in QPSK, now we have a cosine carrier. Also, we have a sine carrier. So we have to have two values. So those two values are coming in here. Now, what's the next thing to do? Serial to parallel converter. What does that mean? We are going to get, let's think about the example of this one. We get 0, 0 input. We're going to get this one, this as a BT, right? So we have a two value in serial. Now what are you going to do? You are making it parallel. And why do you want to make it parallel? The first value goes up. The second value goes down. That's what they mean. Okay, now we have two values, right? One should go up, one should go down. The second one is a sine. First one is a cosine component. So cosine component goes up, sine component goes down. Just split it like that. Okay, that's what's going to happen inside. And once you do that, what's happening is this first cosine term goes up here. So now let's put it here. This term goes up. The second term, let's use this one as an example because this is both are negative, so this may be confusing. So let me use this one as the input. So when you have a 0, 1 as an input, we're going to get these two values here, BT. So negative 1 is a cosine, so that goes up. The second one, positive value, goes down because this is sine component. So sine component goes down here, like that. So right here, we're going to get this value. Right here, we're going to get this value. And what is next thing to do? This is still just the value. In order to transmit over there, eventually we need to multiply carrier, right? Now next thing to do is multiplying carrier. What carrier? Cosine carrier. Why? Because this is a cosine component. You're going to multiply cosine carrier. However, this one, second channel, this is a sine component, right? You're going to multiply sine carrier here. So we multiply cosine carrier, sine carrier here. Okay? Then what's going to be the output here? When you multiply cosine output, cosine carrier, here, right here, your output is going to be this. Right here. What about here? Same way here, you're going to get sine. You actually divide by t, right? Yeah. So that you're going to get sine here. You're going to have a cosine component here. You're going to get sine component here. Okay? Remember that you multiply cosine carrier, and here you get a sine carrier. Once you do that, what do you want to do? You're going to do plus. Just mix these two. Then transmit. Then eventually, what is your transmitted signal? Your transmitted signal is going to be this plus this. This is your S2T. That's what your S2T looks like eventually. Now you have 0, 0 coming in. You do the same way. Then eventually you're going to get minus cosine, minus sine. That's what you transmit over the air. So this is what you transmit over the air. Okay? So your signal actually has a cosine component and sine component. And this cosine component, this cosine, we call that an in-phase channel. Sine component, you call that as a quadrature channel. And a lot of people just call simply that this is I channel. This is Q channel. I means in-phase channel. Q means quadrature phase channel. So we simply call that as I and Q channel. Okay, let's continue next.